So, welcome to today's SERP, Science and Engineering of Radiation Processing, hosted by the International Radiation Association. My name is Thomas Kroc, and I am the U.S. representative and will be your host today. We appreciate you're all taking the time to be here. You're probably all familiar with the IIA, but just in case, the International Radiation Association is a not-for-profit organization that supports the global irradiation industry across all technologies, applications, and sectors. We promote the safe and beneficial use of irradiation and serve as a bridge between science and industry, communicating, educating, and advocating on behalf of our members. These science and engineering and radiation processing events are focused on that cross-communication between science and industry. Membership to the IIA provides access to publications and resources, working groups, visibility opportunities, valuable networking opportunities, and discounted registration fees for IIA events such as IMRP 2027, which will be held in April 12 through 16 next year in Dusseldorf, Germany. To learn more and get involved, you can visit iiaglobal.com or contact us at info@iiaglobal.com. So today's webinar is entitled Advancing Sterile Insect Technique Using Cobalt-60. We're joined by Richard Wiens, who will be sharing insights on this developing situation. Richard is the Director of Business Development and Strategic Supply at Nordion, a Sotera health company. Nordion is the leading global supplier of Cobalt-60 used in the sterilization of medical devices and the treatment of cancer. In his current role, he's focused on developing and implementing long-term strategies for maintaining a reliable supply of Cobalt-60 from reactors around the world and exploring opportunities for strategic growth. Richard has more than 30 years experience in business development, product management, manufacturing, and supply chain in industries ranging from commercial aircraft production to software development. He holds a Bachelor of Applied Science degree in mechanical engineering. So Richard, thank you for your time this morning, and please proceed with your presentation.
All right, let me just click the right buttons here. See if we can get, so that should be, Tom, can you give me a thumbs up that you can see that? Perfect, good. Good, well, good morning, everyone. Let me just move this thing back here so I'm actually looking at you. My name is Richard Wiens. I'm, as Thomas said, I'm the Director of Strategic Supply and Business Development at Nordion, and most recently have become, I won't say I've become an expert on sterile insect technique, but I've learned a lot more in the last week putting this presentation together than I knew for years in advance of that. And the presentation is a little bit mislabeled here in terms of talking about just Cobalt-60. I will talk about other radiation modalities. Of course, the Cobalt-60 is the one that's near and dear to my heart, and it is relevant because we have a current project around sterile insect technique in Mexico, which I think was probably the impetus for this presentation. So without further ado, let me get into the guts here. So sterile insect technique, just a little bit of a primer or a primer, depending on where you're from, around sterile insect technique and what it is. And it's a really interesting application of ionizing radiation. And basically what happens is that you take the pest of concern, whatever that is. We'll talk a little bit more later about a specific pest of concern, but in this case, something that's damaging agricultural crops or livestock or carrying disease, human disease vectors, those kinds of things. And you take that insect and you figure out a way to find some eggs, and you rear those eggs to the pupal stage, and then you give them a dose of radiation. I should say, before you even do that, one of the intriguing things, one of the rabbit holes I got down was, so you've got these insects in the pupal stage. How do you differentiate males from females? Because ultimately you want to give a dose to the males only, not the females. And of course you can't just look between their legs. You need some other techniques for doing that. So there's a whole host of ways that you do this, which I found really intriguing. Males and females are slightly different densities, so some float and some sink, so you can do it that way. You can actually genetically mutate the females so that they become very heat sensitive. So you take this whatever tray or bucket of pupae of the insect of concern, and you give it a little bit, heat it up just a little bit, and the females will die, and you will be left over with just viable males. So there's a whole bunch of really interesting techniques for sorting the males from the females. So once you've got that accomplished and you've got these males in the pupal stage, you will give them a dose of radiation. We'll talk a little bit more about the specifics of that dose. And effectively what you're doing is you're giving them enough of a dose of radiation that you render them incapable of reproducing, but not enough of a dose that you will kill them. So you effectively need to rear them. Then after they've been dosed, you need to rear them to the adult stage, which in this case is typically a fly. They do this with beetles as well, but there's typically a fly. So you have these adult flies, these adult male sterile flies, which you then literally take up into an airplane and dump out of the back of an airplane. Now, in modern day, they're starting to use different delivery methods. So I know in the US, they've been experimenting with drone delivery of these things because they can get a little bit more precision than dumping them out of the back of an airplane. But traditionally, that's what they did. And they would dump, millions of these sterile flies out the back. And what happens is that these sterile males will aggressively mate with females, but they won't procreate. So because they're sterile, they can't reproduce, and you end up ultimately significantly reducing or eliminating the population of that insect of concern, right? And this has been done very, very effectively. As a matter of fact, we'll talk a little bit about the history here if I get to the next slide. So the technique's actually been in use for quite a long time. There are various people around the world that are credited with early science in this regard. There are some Russian scientists and some European scientists, but it was really these two American entomologists. So that's one of the things I had to learn, was to differentiate between entomologists and etymologists, which are people who study words. And they really pioneered this, starting with the idea in 1930, but you can see that it took a couple of decades to really get this down. So one of the things that I would say is the science, the biology around this is incredibly complex. And the radiation part is cool, but I would say it's really the least difficult part of this whole approach. And we'll talk about the other things that go around sterile insect technique. The initial radiation source, back to the comment I made early about Cobalt-60, the initial radiation source was actually X-ray, and likely, I didn't discover this, but I believe it was likely low energy X-ray. And what they found was it worked quite well, but they couldn't scale it, right? So they could do a few of these pupae, but they couldn't do, liters and liters and hundreds and maybe even billions of these insects that they needed to deal with. So they moved to Cobalt-60 for scale because it's highly penetrative, right? It's higher energy. You could do a lot of throughput. And this is maybe somewhat ironic because we're going to talk a lot more about the New World screwworm, which is a terrible sounding thing and looks at least as terrible as it sounds. And the first application of sterile insect technique was New World screwworm. And it was used very, very effectively to eradicate the screwworm in the United States and Mexico and parts of South America. And since then, it has progressed to being used in around 70 countries on 6 continents for a huge variety of pests rather. So again, fruit flies, there's a thing called Mediterranean fruit fly or medfly for short, which is probably historically the predominant application of this for protection of agricultural crops in South America and other places, but you can get, I know we've actually done some work here. So I'm in Ottawa, Canada, where you wouldn't think you have to deal too much with insects because it gets so cold here over winter, but we do have a particular pepper weevil for sweet peppers, for capsicum, that is a problem. And we've actually done some work here on SIT related to the codling moth that is a problem for those pepper crops. New World screwworm we'll talk a lot more about, and then things like tsetse flies, which have this kind of dual agricultural, livestock and human element to them because they're disease carrying, which brings me to the last point, which is that you can use this as well to control mosquitoes that are disease vectors. So for things like malaria, yellow fever, dengue fever, I don't know why I left Zika off this list, but Zika virus was probably one of the more recent applications of this. So where does radiation technology fit into this whole thing? So again, back to the science and research element of this. One of the things, of course, you have to figure out is for a particular pest, what dose do you need to give it in order to render it sterile but not kill it? And you can see from my first bullet there that the range is pretty big. So all the way down to 5 gray up to 400 gray, which of course, any of those doses in the medical device sterilization world are pretty small. They're more akin to what you would give something. 400 gray is what you'd give something in a phytosanitary application if you were, again, trying to either kill or render a pest in a export fruit unviable for reproduction. But 5 gray is a little tiny dose. And it's really dependent on the species itself, whether you're talking about, fruit fly or New World screwworm or beetles or mosquitoes. It depends on the stage. Are you irradiating them in the pupal stage or some other stage, which does happen, and then the age, right? So pupae years are not like human years, so there's a big difference between irradiating at day 1 and day 3 in the pupal stage of a particular insect. So of course you have to figure that out. One of the things that they do in some instances is they actually perform the irradiation in a hypoxic environment, so low oxygen environment. And this has this interesting kind of double-edged sword radioprotected effect, which is that you can manage to get a dose to the reproductive cells that is either lethal or damaging enough that the reproductive cells don't work anymore, but the actual hypoxic environment protects the rest of the insects so that it continues to be viable. So some really interesting science there. In terms of scale, there are small scale facilities, but there are also very large scale facilities, right? And again, this tends to be where Cobalt-60 is used, and these facilities would be rearing hundreds of millions or billions of insects per week. So there's a joint program with the United States and Panama and Guatemala and a couple other countries called COPEG. And there's a facility in Guatemala, and I don't know that they're currently at this throughput level, but I found a source that told me that at peak throughput, they could actually produce 2 billion med flies a week, which is 20 tons of flies, which is an awful lot of flies, if you can imagine. So clearly you have to be able to irradiate large volumes for programs like that. You can do this in self-contained, low energy X-ray machines. So that RadSource machine there, if you go to their website, that machine is specifically marketed as a machine to be used for SIT, maybe other things as well. But on the website, they have a SIT example, and it's actually got, I forget, 5 or 6 horizontal canisters arranged inside that door to be able to give some low energy X-ray to. The one below that is what's called a Gamma Cell 40, which is a product that Nordion used to build before we sold that company to Best Electronics. That's a cesium-137 based irradiator. Those are being phased out, as many people know, but there are still some of them left over. And one of the things you can do is with that irradiators to use it for SIT. And then on the right-hand side, another self-contained irradiator, Cobalt-60 base, this time that Nordion produced back in the day, called a Gamma Cell 220. And it's called a 220 because its radiation volume is 2.2 liters. So you can deliver a nice dose to that, a nice uniform dose, and in a relatively short period of time, again, because the dose is so low, right? If you're talking about, 10 or 20 or 50 gray. The large-scale facilities, and I did not find a large-scale facility that wasn't Cobalt-60 based. So my belief is that the current full-scale industrial irradiation facilities for sterile insect technique are Cobalt-60 based at the moment. And again, that's because of the high penetration and the ability to have a very large throughput. Things like industrial Linacs would have potentially a higher throughput because of the higher dose rate, but of course the pupae would have to be presented differently, right? You're not going to get an e-beam through a foot of high density larvae. So typically Cobalt-60 is used for that today. But to my last bullet point, I know there's a lot, maybe he's even on here, I know there's a lot of research being done at places like Texas A&M with Suresh Pillai and other folks who are looking at being able to use e-beam or higher energy X-ray for this application. So the current pest of concern, and again, they're probably the impetus for the interest in, or the resurgence in interest in this application of ionizing radiation, is something called the New World screwworm. I can't pronounce the whole Latin name there. I just can tell you that anything that ends in vorax just seems like it's ugly, and it is. You can see the actual worm on the right-hand side here. Now, I realize that some people are close to either lunch or dinner, so I've spared you the gruesome pictures of infested cattle. But basically, the reason that this is such a big deal is that the female fly will land in an open wound on a beef cattle and other animals, but the beef cattle are the primary livestock crop of concern here, will land in an open wound, lay eggs. The eggs will basically hatch into that ugly looking guy there, the maggot stage, and they will consume the flesh of the animal, and it can lead to very bad infections and ultimately in death. And of course, nobody wants to eat cattle that have been infested that way. So as I mentioned at the beginning of the webinar here, the sterile insect technique was actually first used for New World screwworm, and those two pioneering scientists developed that program such that they were able to eradicate the New World screwworm, and I'm just going to call it NWS because it's hard to say, eradicate the NWS in the 1960s. I forget, it was 1966 or some date in 1966 where they declared it eradicated in the US. Mexico in the 1970s. They kept basically moving it in, moving the barrier further down into South America to the point where they were able to establish this kind of beachhead around Panama, because of course that's kind of a skinny area. You don't have to eradicate it over a very large geographic territory. So there's this thing called the Darien Gap, where they've created this living firewall, and that's in part due to ongoing SIT programs that are run in many of those countries. It is endemic. One of the things that I learned, and I'll mention this at the very end, there's one of the interesting things that's come out of this is that the American Nuclear Society has stood up a task force around this, because of course they're interested in promoting the sort of the peaceful use of nuclear technology, and they've stood up a task force, and they've they've really sort of pulled together all of the experts in the industry that have anything to do with this. And there's been a lot of conversation about, how do we keep this thing from resurging in the US? So that was quite interesting to me. So the current situation and sort of the reason again for this resurgence of interest in the technology and the application more broadly is that there's been a resurgence. First started in 2023, in the 2023 timeframe. It started in sort of Central America, moved into Mexico. By July of 2025, it had not reached the US yet, but it was prevalent enough in Mexico that the US imposed a ban on Mexican beef imports in July of 2025, so effectively a year ago. And this has had, by the reports that I was able to find, about a $2 billion impact on the Mexican cattle industry. And because there's so much, and I forget the number in terms of the number of pounds or kilos of beef, but it's a lot of beef that would typically come from Mexico. So of course, not having that Mexican beef has driven up prices in the US for Mexican beef prices by huge amounts, like again, 60 or 70% or something like that. It's been crazy. Now we have very, very recently, like that is what, two weeks ago, had the first case of NWS detected in the US. That the bottom right-hand corner map is kind of the broader geographical map of where these cases are, both active and inactive cases. And then that top left-hand corner, there's actually a dashboard. So the United States Department of Agriculture, the USDA, has a division called APHIS, which is Plant Animal Health Protection. I don't remember the exact acronym. They actually have a dashboard. So if you can't sleep at night and you want to find out where NWS is, you go to the dashboard and it'll actually tell you where the reported cases are. That map that I put up there is from 3 or 4 days ago. So those are cases, and they're not a ton of cases, right? They're kind of here and there. But it is in the US, so there's a huge amount of interest in this. To the point that the USDA has announced, I believe the funding level for this was something like $750 million to build a new SIT facility. I don't think exclusively for screwworm, but I think that's one of the intended cases so that they can be kind of self-protectant. And the capacity objective there is to have a facility that's up and running and being able to rear 300 million flies a week by 2027. I don't know a lot more about that program. I can't tell you because I don't know which technology they are intending to use in that program. I do know that they've also made an investment in Mexico. So Mexico has a very active SIT program. The US is making I can't remember the number, $25 million investment in kind of upgrading some of the Mexican facilities to be able to provide bigger output, particularly in the case of screwworm. And then there's also a lot of interesting science research and science going on around kind of non-SIT or non-ionizing radiation approaches to sort of population control. And again, I'm not an entomologist or biologist, but it feels to me like there's a lot of sort of genetic manipulation and those kinds of things. So same end objective. So the idea is that you would release sterile males into the population and therefore drive down the population. But there's a bunch of interesting things. I think those are relatively early days, and quite frankly, the SIT application works so well. It's been so effective, generally speaking, that I think it would take a while for that to get displaced by some other kind of approach, some other kind of science. In terms of what we're doing, and again, I think this was part of the impetus for the webinar, was we put out a paper a month ago or so around a project that we're working on in Mexico. we've built Nordion's built, as most of you probably know, one of our lines of business is the design, construction, fabrication, commissioning of large-scale irradiation facilities. We've built, of the 300 or so operating in the world today, we built about 135 of them. We continue to do that primarily in Europe and Asia and other places. We built two purpose-built irradiators for SIT. For an organization called SENASICA. You can see the acronym there in Spanish, but it's basically, as I've spelled out, the National Service for Agricultural, Health and Safety and Quality. So SENASICA have built and operated these two irradiators. The first one was built in 1978. You can see I've got a really retro brochure there for something called the JS7400, which is probably our second generation of tote box irradiators. People who are old enough will remember that the very first Nordion tote box irradiator was something called a JS6300, and the rumor is that it was called a 6300 because at the time it cost $63,000 to build. I don't know if that's true or not. I don't know if the 7400 cost $74,000 to build, but the JS7400 was built, and both of these, by the way, are on the same campus I think I've got it there, yeah, Metapa de Domingo, Mexico, which is in Chiapas State. And that this is a very large campus whose sole purpose is SIT. And we built that 7400 in 1978, and then in 2018 we built something called a Gamma Fit. So the Gamma Fit is intended to be sort of a modular irradiator where you can build a shield, and over time you can start with a simple pool, wet storage pool panoramic irradiator, and you can upgrade that to a batch tote and ultimately to an automatic tote, which is actually where we started with this one. So we built those two facilities. And when this outbreak of New World screwworm started in Mexico and ultimately moved to the U.S., of course, there was a lot of interest in getting this kicked off. And again, I don't know the extent to which these facilities were already producing sterile flies, but they needed some work in terms of upgrading so that they could get into high capacity mode. So we launched a project, and it's an interesting kind of bilateral trade project because this was helped along in part by the Canadian government, who has a trade relationship with Mexico. And they approached us and asked if we would effectively be able to fast track some engineering help for upgrading these facilities. So we sent a team down there, and they put together a proposal to upgrade various elements of the irradiator, including controls and safeties and mechanical equipment. And I believe there's some work on the pool that's being done as well. So we actually have a team. I think they might even still be down there. They traveled to Mexico, I would say, in the last couple of weeks to perform at least one phase of this upgrade, and then the objective is that they would get back into production, large scale production. One of the things that I didn't mention in terms of technology and particularly placement of the irradiator is that the irradiators in these large scale facilities are co-located with the rearing facilities. And my understanding is that one of the bottlenecks, so put it this way, the bottleneck typically has not been the irradiation capacity. So there is enough irradiation capacity, and particularly with these upgrades, where you can irradiate quite a large volume, that 20 tons that I talked about before. You can irradiate that. The bottleneck comes in the rearing facilities. So it's quite a trick apparently to rear these things and get good yields out of them, right? There's all kinds of opportunity for the insect to die along the way. And so the rearing outside, the rearing before and after the irradiation tends really to be the trickier part of the process. But one of the challenges, of course, is you've got these irradiated insects. You don't necessarily want to be putting them on a truck to cart them hundreds of miles away to a rearing facility. So the large scale facilities, the irradiation, the ionizing irradiation facility tends to be located with the other one. So that's effectively what I know about sterile insect technique and our project. And it's been fascinating learning a little bit more about this. I knew the basics before. I would say, I think I have a slide here with resources. If you are curious about this, there's all kinds of resources out here. In particular, I would point to the top one there, the American Nuclear Society, who's stood up this task force and actually has built a whole microsite around screwworm and the application of ionizing radiation for control through sterile insect technique. The IAEA has been a big supporter of SIT around the world. This is kind of one of the areas that they do a fair bit of work in technical cooperation. They also have a good set of resources there. Senasica, which is the Mexican government agency that owns and operates those two Nordion irradiators I referred to before, has some good stuff. You'll have to translate that stuff. It's in Spanish. APHIS, the USDA, Department of Agriculture group that manages these things, has a bunch of interesting information on there. And then COPEG is this, again, joint US, Guatemala, Mexico, a bunch of other countries in their facility, which I believe is in Guatemala, and they have some other interesting resources. So again, I hope that was helpful. I hope you learned a little bit of what I learned in the last week or so. And Thomas, I will turn it back to you for, I guess, some questions and answers and discussion.
Okay, thank you so much, Richard. That was impressive. So one of the points of SERP is to provide plenty of time for Q&A and discussion, ideally to create a community that gets together regularly to talk about random topics in the radiation processing. So you can either unmute and ask your question verbally, or you can put it in the Q&A. So I'll ask one. As you mentioned, those doses are really low, and with a panoramic irradiator, such as what you produce, does that pose any particular challenges to consistently, with good accuracy, give such a low dose?
I don't think so. So the way I would answer that is you would have a challenge, and we see this in the phytosanitary world, right? Where those doses kind of start at the high end of the SIT range. So if you're trying to deliver a 400 gray dose in the same irradiator where the next day you might try and deliver 25 kilogray with cobalt, then that presents a certain set of challenges. But these irradiators are purpose built for delivering low dose, so they simply have a lower level of activity than you would find in a large industrial scale irradiator, right? So I would argue, yes, if you had an irradiator with 5 million curies in it and you were trying to deliver 5 gray, you would have a problem. But these irradiators don't have anywhere close to that. So for that application, it's not an issue. And I asked the engineering guys, I have them written down there, the tote dimensions, they tend to be relatively small totes. So you can get things like reasonable dose uniformity, right? They're not massive, 2x4x6 totes. They tend to be a relatively smallish volume, so you can get good dose uniformity, again, with a relatively low activity. But that's a good question. Yeah.
Okay. So we've got one in the Q&A here. Could you please describe in further detail what you mean by rearing?
Well, now you've got me, because that's the sum total of my knowledge, is that you need to rear them. So I believe
it's basically growing. I mean,
Yeah, it's
right?
basically growing, and I would have to guess that you are trying to control environmental conditions, and I used to know a lot more about this than I remember. But you're trying to control environmental conditions, and you have to feed them too, right? So I don't know. I have no idea what New World screwworm pupae food looks like and where you get that. But they need some level of nutrition. They need they need proper, conditions in terms of light and temperature and humidity, and all of those kinds of things. And I couldn't find a good picture, but I have seen pictures of these rearing facilities, and they kind of look like, my recollection is if you've ever seen a picture of a commercial bakery, they have these big stainless steel racks with all of these trays, and these trays are full of these pupae, and they're in, they're in a big building that's got those environmental controls, and there's a lot of science about, you know, about again, what you feed them, what temperature you keep them at, all the rest of that kind of stuff. I don't recall how after these things emerge as flies, right? Because it's really the fly stage where you take them out and release them into the wild. I don't know what happens after these things hatch into flies, and how you collect them up and keep them contained. But there's a whole big a bunch of science and engineering around that. But I would encourage you to. I mean, some of the resources I put up there, I just didn't get deep enough into it. But some of the resources are, you should be able to find that. And I'll suggest to the ANS guys that they should put some of that stuff on their website, because I think that's to me that's equally as fascinating as the radiation part, right? It's like, what's your job? Oh, I made a billion flies last week, right? So. Um,
Yeah, well, I guess it's interesting because you want to isolate the males so that you can sterilize them, but you have to rear also enough females so that they can produce
yes,
the next generation that you
yeah,
have to.
yes.
So,
So they do some of that, and I think that approach has actually changed. I know the Seneca guys corrected me when I at one point when I talked about males, and they said, yeah, we do females as well out there. I don't know. There's some magic ratio. I can't remember, like 10 to 1 or something like that. But they do raise some females. I think in the early days they didn't do that. They just assumed that there was enough female population in the wild, that they would be able to control it. But I think they've kind of advanced the science now that they understand that you do need to actually release some females as well. So it's quite interesting.
well, I mean, just internally. I mean, if you're going to produce 2 billion
Yes,
flies a
yeah,
week,
absolutely. Yeah, absolutely. Yeah, yeah. You need somebody laying eggs. Absolutely.
right?
Yeah, yeah.
So, okay. So you talked about in the rearing facility, um, making sure that nothing escapes in that. Um, when in designing the irradiation facility, any special accommodations there to that you know
I
of?
don't, I don't believe so. Again, I think the focus was on, sizing the tote, sizing the irradiation volume such that you could get good DUR. They may even have internal specialized carriers that they use within the tote for that. I don't recall. I've never been to this facility, so I've never seen the machine. Um, so I think that was one thing. Yeah, I think it's like any of these things. I mean, they're relatively dense, right? If you think about this compared to, some of the lighter medical devices, right? You've got reasonable volumes of pretty dense stuff. So things like handling them, right? I would have to imagine that these containers weigh, way more than you would comfortably want to be hauling around by hand. So there's probably some interesting conveyance mechanisms to get them from place to place. But From the irradiator standpoint, there wasn't a lot of specialization that I knew about.
Okay. I'm going to actually put one of our attendees on the spot here because I know they expressed a particular interest, and we're having difficulty registering. But Joseph, any particular reason that you guys all wanted to view this?
Yeah, we're looking into just the marketplace of Cobalt-60 and as an emerging just an emerging threat with the new screwworm, and we're seeing facilities pop up around the world just to understand the the market of this phenomena. And obviously, we're seeing on the news, we're seeing the day by day, blow by blow accounts of how far north it's coming, and just to keep the Office of Radiological Security appraised of what the industry is doing to solve this problem.
Sure.
Okay.
So
Yeah, I would have to say, I mean, this is my perspective, is that because of the investment required on the rearing side and all of the infrastructure, you're likely to see fewer centralized facilities than distributed facilities, right? So if the query is around, hey, are you going to see 100 facilities with 100 curies in them each pop up around? My take is you're not going to see that happen, right? They would either upscale existing facilities again. I don't know. I only kind of read about this USDA facility I want to say it's in Texas somewhere. Maybe that was in one of my slides that they're planning. I don't know what technology they're planning to use for that from an ionizing radiation perspective. So that's my take, because I don't think you'll see people popping up gamma cell 220s in part because you can't get them anymore.
right.
Around the country to do 2 liters worth of larvae at a time. That's my take. So I'm not close to the program, so.
Well, and another thing of interest to us is too, we just saw that it was Google, I believe, just applied for a permit in the U.S. with the USDA to do something similar with insect incompatibility. So they're introducing a bacteria into flies, and they're going to release them down in Florida. We're curious to see how you guys feel the different modalities are going to work together. Is one going to become dominant, or even CRISPR technologies we're seeing too, which we're seeing. I don't know. Do you have a take on that?
I don't really. I mean, my reaction to that, which I think I kind of articulated earlier, is, hey, we've got these facilities, these large scale facilities, they're being upgraded. Cobalt, there's not a lot of cobalt in them, quite frankly. I have the installed numbers here somewhere, but it's like 100,000 curies of cobalt up to, I think the one facility is licensed for 1 million or 1.5 million or something, which would be the absolute top end. So you don't need a lot of cobalt to run these things. The technology and the application is super well understood. All of the infrastructure is there. It's hard to imagine in the short term that somebody, and the program that you just referenced, I did hear about that. We convened this ANS task force last week, I think, for the first meeting, and there was somebody on there talking about that technology, which was super fascinating. But it sounded again like it was relatively early stage. So so I mean that's what I know. It just seems like the incumbent technology's got a fair bit of inertia behind it. So.
Yeah, thank you. Thanks for the feedback. Appreciate it.
You mentioned early in your presentation that, to your knowledge, all the active facilities were cobalt-based. When I was researching this a few years ago, I think it may be in the IAEA database. There may be a facility in Spain that uses a rototron. But I wasn't able to find much information about it, and I don't know if it's currently active or whatever. So
no, I couldn't find it. I mean, I know about the research that's gone on at, for instance, Texas A&M. I know there are commercial e-beam facilities that are interested, and some even sort of close to the border that are interested in sort of participating in the project. I don't know of any that are sort of actively irradiating anything at this point. So, and that may well change as this thing progresses, or hopefully doesn't progress. I mean, the ideal is that so somebody said that. They said that's the absolute wrong answer, is to build a big facility in the US, because that means that you've lost. And hopefully, you can do something in Mexico and South America, points further south, where you don't have to do anything in the US because you've managed to get it under control, right? So
Yeah.
I have some interesting notes. Protocols like every time they have an outbreak in the US, they have a certain volume, and it's a lot, right? It's like, I want to say like, a couple million flies released I think like an 8 or a 20, I think it was 8 million flies released in a 20-kilometer radius around where the discovery was, right? So they've kind of got it down to a science about how you manage this thing. It's super, super fascinating, area for sure.
Okay, one last time for any further questions, either verbally, raise your hand, put them in the Q&A. If I don't see anything, then we will call it a day. And again, Richard, thank you so much.
Yeah,
Very
no trouble.
fascinating presentation. And so thank you all, and we'll see what we come up with for next month or so. So keep your eyes peeled on the SERP LinkedIn page, and we'll announce it when we come up with something. So thank you all.
Awesome. Thanks, everyone.
Thank you. Appreciate this.